This video is going to take us through energy changes in the chemical bonding process, and we're going to talk about reaction rates also. Because when a chemical reaction occurs, it's not just simply a matter of rearranging the molecules like we talked about. There's also an energy transformation that can take place as well. All right, and so move this. I'm going to get this thing out of here just so it's out of the way. During a chemical reaction, energy is either absorbed by its surroundings because it needs more energy to form the new bonds. And so what will happen is that it will absorb energy. It will absorb energy from the surroundings to break the bonds and to form the new ones, or less energy is needed to form the new bonds. And so energy will get released into the surrounding environment. All right. And so we're going to look at these two energy transformations that take place. All right. One of them is called an endergonic reaction. All right. And this is a reaction where energy is absorbed. All right, so like something like this would be like a reaction would be like photosynthesis, DNA growth, protein synthesis. These are all examples of energy being absorbed during a reaction. Basically, more energy is needed to create the new bonds that are created during the reaction, so it'll absorb more energy from its surroundings. Okay, so since more energy is needed to create the new bonds created during the reaction, that energy has to come from somewhere. It can't just be made up. So what happens is a lot of times in an endergonic reaction, energy is absorbed. It's taken in. Okay, so in an endergonic, it kind of sounds like in. It's taken in. All right, and one of the specific examples we're going to talk about is an endo. Energy is taken in. Endothermic. Thermic means heat. Energy from the surrounding environment in the form of heat is absorbed. So like an endothermic reaction is a type of endergonic reaction, but it's specific to heat. And the surrounding environment will become cold. All right. So if you think of like an athletic ice pack, when that breaks, what happens is that that package becomes cold because for the reaction to form the new bonds, more energy is needed once that reaction occurs to form the new bonds. So thermal energy is absorbed to help create the new bonds that is created during a chemical reaction once that once that reaction is initiated. More energy is needed to form the new bonds that are within that, so then it becomes cold. All right, so that's a practical use for like an endothermic reaction. All right, and an endergonic or endothermic reaction looks like this graphically. All right, because we're going to look at some graphs later on. Well, you'll have the reactants. Right, you'll have like as the reaction goes on, you'll have the reactants here. Here's energy on the side. As the reactants go up, let me see if I can get. I can't do that. As the reactants go up, as the reactants occur, the products increase in energy. All right, so basically it's an uphill, if you can look at it just in terms of like this, it's an uphill reaction, all right, where you have more energy in the products. Once again, energy is on the side. You have more energy in the products than what you have in the reactants. That energy got absorbed from the surrounding environment. So as you go uphill, more energy was needed to form the new products than what was the reactants for. You might be like, what's this little bump right here? All right, that's just activation energy. That's something to activate the reaction. Typically, you get a spike in energy and then it'll come down. So don't worry too much about that. And then sometimes we'll look at it in equations. If we look at it in equations, you'll see energy, and I got an equation down here also. We have energy is on the reactant side because more energy is needed to help form the new bonds. All right, so energy. So if I give you an equation on the test and I say, hey, is this an endothermic or exothermic reaction? Just pay attention to where the energy is. If it's in the reactants, it means more energy is needed to help break apart. In this case, it's aluminum oxide. More energy is needed to help break apart aluminum oxide to form these new bonds that are created. All right, so more energy is going to be needed to break apart the bonds to form the new products. Whoop. Clear. An exergonic reaction is the opposite of that, obviously. You think of energy as exiting. All right, less energy is required to form the new bonds than is required to break the old bonds. So the surplus energy gets released. Think of like a glow stick. You crack that glow stick, well, less energy is needed to form these new bonds. And so light is given off, energy in the form of light. A firework is given off, is an example of an exergonic reaction. You have a surplus of light. Once that reaction occurs, sound, there's a surplus of energy that is released because not as much energy is needed to form the new bonds. And exothermic is exactly what it sounds like. Heat is exiting. Thermic is heat. Exo means it's exiting. All right, so an exothermic reaction is when heat is given off. So the surrounding environment will feel warm. All right, so when we do this in labs, because we can't really see what happens on a molecular level as well with the energies, but when we do these in labs, an endothermic reaction is going to get colder. So when you observe the temperature of the surrounding environment gets colder, that means energy is needed. It's being absorbed to help these new bonds form. All right. Whereas an exergonic or exothermic reaction, the surrounding environment is going to get hot because that extra energy is being released into the surrounding environment. All right. So when we do these in labs, that's what we're going to focus on. And then sometimes you'll look at it graphically. Once again, heat is being released. The product is down. It's a downhill reaction. You have more energy in the reactants than you have in the products. All right. If you look at it in an equation, energy will be produced. Once again, remember, an equation is you have something new is being produced. What's being produced? When hydrogen and oxygen gas produce water, well, extra energy is produced. All right, so that's given off. That's produced in the product. So if you have energy in the product side, that means extra energy was produced. It's a product. It was created. So that's an exothermic or exergonic reaction. All right, because the products have less energy needed than what was needed, than what the reactants had. Less energy was needed to form these new products, to form these new bonds. All right. And so those are the two types of reactions, and we'll look at that in labs. Once again, heat, if heat is given off, it's exiting, it's going in the surrounding environment. If heat is absorbed, it is taken in. It's an endothermic reaction. All right, rates of reaction. We have catalysts used to speed up a chemical reaction without permanently changing. That's a vocab term that we have. Now, the mass of the product forms, it's the same, remains the same because it doesn't actually become a part of the reaction. All right, but it will help it form more rapidly. All right, so it doesn't become a part, it just expedites the process. All right, this is called elephant toothpaste. All right, you have two things reacting together very quickly. All right, you have a catalyst to help that reaction occur very, very quickly. All right, and so a catalyst is something that can speed up a chemical reaction. It makes it go faster. All right, so catalysts are used to speed up chemical reactions. And these will be used. We'll look at this as well. We'll look at a catalyst lab with this as well. Inhibitors, on the other hand, they will prevent or slow down a chemical reaction. If you think of like food preservatives or things like that, that's an example of a chemical reaction because it slows down the process. Food spoiling is a chemical reaction. It slows down that process of a chemical reaction. Like things that prevent rust and things like that also will do that as well. All right, those are inhibitors. They either prevent it or they will slow down the process. So there's a lot of practical uses for those as well.